In order for a chemical reaction to take place, you have to have particles colliding. The collisions that happen are linked into an idea called collision theory. Now, not every single collision between atoms leads to a reaction. We can relate this to human beings. Human beings bump into lots of different people, but that doesn't mean that they're going to strike up a conversation or develop a friendship or develop a relationship with various people, every single person that they bump into. So what you have to have is you have to have what are called effective collisions. In order for a chemical reaction to take place, the collision between the particles has to be effective. Now, by colliding, I'm saying that, for example, if I had a oxygen molecule and I had a little hydrogen molecule and they were to meet up with each other, kind of need to have two hydrogen molecules there, and they met up with each other, I would land up with two water molecules, let's say. How does that happen? How do we get from these reactants into these products? Well, in order for that to happen, I need this oxygen to bash into this hydrogen and this hydrogen to bash into that oxygen in exactly the right orientation and with exactly the right energy in order for the reaction to be an effective collision. So, what's important is how do we get them to correctly orientate? It's kind of the same as if you were to bump into another person with your back, you probably wouldn't have an effective collision. It wouldn't result in a conversation being struck up or anything. You need to be facing each other and then you're going to have an effective collision. In order to make a reaction go faster, because remember what rate is the speed of the reaction. So if we want that reaction to go faster, all that we need to do is we need to increase the number of effective collisions. Now, it's difficult to increase how effective collisions are. A catalyst is quite good at turning the atoms so that they are in the right orientation, literally getting them to be in the right positions to react. But other than a catalyst, the best way to get lots of effective collisions is just to get lots of collisions. And the way that we get lots of collisions is to make the particles bash into each other more often. How can we do that? There are a whole lot of different ways. The first way is if we had gas particles and we squashed them close together, then they would bash into each other more often. It's kind of like if you were to go to a party and you were there were only 10 people in a very big room, you're unlikely to meet anyone that you didn't know before. But if you are at a place where there are lots of people in a small space, you are more likely to collide, and therefore, if you're going to collide, there are going to be more collisions, more effective collisions, and therefore that results in a faster rate of reaction because the particles have been pushed close together. How's temperature going to help us? Well, temperature, remember, is a measure of kinetic energy. Kinetic energy is going to make those particles move faster. If they are moving faster, they are more likely to bump into each other. The same as if you were walking around a room, you are likely to meet more people than if you just stayed in one place. So the faster you move, the more likely you are to collide, and therefore the more likely there are to be effective collisions. What about concentration? Concentration means that there are more particles in a smaller space. And the same as pressure, more particles in a smaller space means that there are going to be more collisions. If there are more collisions, then you land up with more effective collisions. And more effective collisions means it is faster. It's important to note that the change in pressure will not affect solids and it will not affect liquids because that won't bring the particles any closer together. A change in concentration does not affect solids because the particles don't come closer together. So concentration is only a factor that can change the rate in solutions and in gases. Pressure is only able to change the rate of a reaction in gases. If I want to change the rate of the reaction in solids, I need to look at a concept called state of division or size of reaction surface. In other words, how crushed up, how small is it divided? So this is how crushed the particles are. So if I, let's say, have a big block over here and I'm trying to react and I'm approaching this crowd from all angles, the only people I'm going to meet are these ones over here. However, if I have got a whole lot of small little particles like that, and I'm approaching this crowd, I have an opportunity to meet that guy, that one, and that one. If I come from this side, maybe I'll meet somebody here, somebody here, somebody here, somebody here. Same if I come from that side, I can meet over there, over there, over there, over there. And what lands up happening is that there are more particles that encounter one another. So it's more particle encounters, and therefore you land up with more collisions, and more collisions will mean a faster rate of reaction. We discussed catalysts a little bit earlier, very briefly, but basically a catalyst turns the atoms so that they bump into each other correctly. It lowers the energy required to be able to get to the activated complex, and that way makes everything work faster. And then also, it depends what you're reacting. There's certain things, for example, if you put magnesium and oxygen, that reaction proceeds really quickly. But iron and oxygen proceeds much more slowly. So exactly what are you reacting has a lot to do with how fast that reaction occurs. This is a Maxwell-Boltzmann distribution curve. And what it does is, if we look at the axes, I've got kinetic energy increasing and I've got the number of particles. So in a certain vessel, I will find that, let's say it's 300 Kelvin, that lots of particles have got hardly any energy at all, and fewer and fewer and fewer and fewer particles have got higher and higher energy. Remember, that's higher energy, and that's my number of particles. When I'm at 400 Kelvin, I find that more particles have got higher kinetic energy, more particles have got higher kinetic energy at a certain temperature. So at 400 Kelvin. So what we're going to do is we're going to say, if that's the activation energy, only the particles with that much energy can react. So what happens is that if you have a cold solution, let's say 400 Kelvin, then there are very few particles that have enough energy to react. If your solution is hotter, let's say 400 Kelvin, the number of particles that could have enough activation energy is higher. So temperature is an indication of the average kinetic energy of all the particles in the system, and the higher the temperature, the average energy of the particles is going to be higher. Some particles in the system have less kinetic energy and others have more. Only the particles with an energy beyond this activation energy line are able to react. There are lots of different ways of measuring the rate of a reaction. We can measure how the reactants appear and disappear, the different color changes. So, for example, a solution gets lighter and it changes to clear. Or you can say it's light blue, very dark blue, and you can use color cards, or spectrophotometers. And spectrophotometers are able to see how well light passes through solutions. You can see how well a solution conducts electricity to see if there are more ions or less ions in the solution. You can see how much gas has been produced, what volume of gas has been produced. We can look at the change in mass of either the reactants or the products. We can look at how much solid has been formed, what is the actual volume of solid that is being formed, and how fast is that happening. With all of these, we look at how fast we are either seeing reactants appear, seeing reactants disappear, seeing products appear. How fast is the color changing? How fast is the conductivity changing? How fast do we produce a certain volume of gas? How fast do we get a certain mass of substance? How fast do we get a certain volume of substance? Turbidity is often used, and that is precipitate formation. And what that is it's almost the opposite of a color forming. It is when, instead of a solution changing color, it actually becomes opaque. And opaque means I can't see through it any longer. So if it becomes opaque, at that point I can say, I can stop my chemical reaction. And we can measure the rate of the reaction. After reviewing the definitions and the factors that influence the rate of a chemical reaction, on the next slide you need to watch a number of videos that show you how various factors influence rate, and take a look at some of these different factors that can be used to measure changes in rate.
The rate of a chemical reaction is defined as the change in concentration per unit time of either the reactant or the product. Factors which affect the rate are, when you're dealing with a solid, surface area, a solution or a gas, concentration, pressure, if you are dealing with just a gas, the temperature will affect all phases, and if you add a catalyst that can make the reaction go faster.